Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Synthetic methanol production explained. From Syngas to liquid fuel methanol industry capacity is about 110 million metric tons/year globally, across 90-plus plants. Modern plants mainly use natural gas, coal, biomass, or captured CO2 plus green hydrogen. Methanol looks simple: CH₃OH. 1 carbon, 4 hydrogens, 1 oxygen. But this small molecule runs a huge industrial chain: formaldehyde, acetic acid, plastics, fuels, solvents, and now even low-carbon shipping fuel. Methanol was once called wood alcohol because it came from destructive distillation of wood. In 1923, BASF developed the first industrial synthetic methanol process using high-pressure, zinc chromite catalyst, around 300 to 400 degrees Celsius and 300 atm. Synthetic methanol means methanol made by chemical synthesis, not fermentation. The heart of the process is simple: make syngas, then convert syngas into methanol over a catalyst. Every methanol plant is basically a chain of reactors, compressors, heat exchangers, separators, and distillation columns. Natural gas is the cleanest fossil route. Methane reacts with steam inside catalyst-filled furnace tubes to produce hydrogen and carbon monoxide. Coal gasification is widely used where coal is cheap, but it produces much higher carbon emissions than natural gas methanol. IEA notes coal-based chemical production, especially in China, is a major emissions challenge. Green or e-methanol uses renewable hydrogen and captured CO2. As of March 2026, announced renewable methanol projects tracked by the Methanol Institute reached 48.5 metric tons per year by 2031. The reactor needs the correct hydrogen-to-carbon balance. Too much hydrogen wastes compressor power. Too much carbon oxide lowers conversion. Operators adjust the Syngas ratio using reforming, CO2 addition, or water gas shift. Catalysts are sensitive. Sulfur, chlorine, oils, dust, and metal carbonyls can poison the catalyst. Before entering the reactor, syngas must be cleaned to very low impurity levels. Methanol synthesis happens under pressure. Modern copper-zinc catalysts commonly operate around 30 to 100 atm and 200 to 300 degrees Celsius. Inside the reactor, syngas flows over Cu/ZnO/Al2O3 catalyst. Copper activates carbon oxides and hydrogen. Zinc oxide supports catalyst activity and stability. Methanol synthesis is exothermic. That means heat is released. If temperature rises too high, catalyst life drops and side reactions increase. Heat removal is critical. Large methanol reactors often remove heat by generating steam. This improves efficiency. Reaction heat is not wasted. It becomes useful plant energy. Only part of the gas converts in one pass. So the plant condenses crude methanol and sends unreacted gas back to the reactor loop. Crude methanol contains water, dissolved gases, ethers, ketones, and higher alcohol traces. Distillation upgrades it to commercial-grade methanol. High-purity methanol is usually around 99.85% methanol by weight for commercial-grade AA applications. It must be stored carefully because it is toxic, flammable, and absorbs water. Natural gas methanol can have life cycle emissions around 2.05 to 2.20 kilograms CO2e per kg methanol. Current global methanol production and use causes roughly 0.3 gt CO2 per year, according to IRENA. Methanol is not just a chemical. It is a platform molecule. From one liquid, industries produce formaldehyde, acetic acid, olefins, fuels, resins, coatings, and synthetic hydrocarbons. In 2025, a commercial-scale e-methanol plant opened in Denmark with annual capacity around 42,000 metric tons, using renewable energy and captured CO2. Synthetic methanol production is a perfect example of chemical engineering, reaction chemistry, thermodynamics, catalysis, heat recovery, compression, separation, safety, and sustainability, all working together to turn gas into a valuable liquid molecule. From wood spirit to green fuel, methanol is one of the smallest molecules with one of the biggest industrial futures.